programs designed specifically for the unique challenges of the sector, while also providing an overview of the current state of play of the broader non-terrestrial network market. We also want to hear your thoughts and questions. You can pose your queries to our speakers using the box underneath the main presentation, and we will aim to cover as many as possible later in the session. So, without further ado, Tim, I will hand it over to you.
Thanks very much, Michael, and great to be here. So, my name is Tim Hatt. I work in the GSMA analyst group called GSMA Intelligence, and the non-terrestrial network story has become such a key focus area for us as it has the wider telco sector, the last 2 years in particular. And so I wanted to share some of our analysis on that to set the table for this discussion. So I'll talk for about 10 minutes and go through what are some of the key factors driving this space and what the outlook looks like. I think the first point to make is that the capacity increase from satellite is an order of magnitude of what it was. Since the original SpaceX filings in 2016, a host of kind of competition has come to the fore, and has announced plans for launching satellite constellations that will translate into a footprint that is just 5 or 6 times what it has been historically. You can see that on the chart here. This kind of hockey stick style line that's in teal shows that towards the end of the decade we'll be well over 10,000. Indeed, if you took that forward to 2030, it would be over 15,000 satellites, dwarfing anything in the past. That's really come about by an improved cost structure of launching and maintaining satellites, and also better performance at the lower altitudes that has been possible in the past. And I think the other point to make here is that non-terrestrial networks has a whole variety of options, all being innovated on and pushed. High altitude platform station, HAPS, also very much in the frame. In addition, to the satellite constellations we're talking about today. If you look at I think it's important to understand the underlying use cases that satellite seeks to serve. We think of those both in consumer and business. So let me take the consumer side first. The coverage gap is one of the main barriers to connectivity that still exists today. It is smaller than it used to be, given that mobile coverage reaches about 93% of the population worldwide. The problem is reaching that final 6 or 7%, what we call the final frontier, has a set of prohibitive economics against it, which means that terrestrial expansion is very difficult. And therefore there is an opportunity to infill that coverage from the sky. This is a table showing the unconnected population actually 2 years from now. And even then you have sort of almost 8% of the world, that's 7.7 at the bottom. Whilst this is, as a share of population, highest in sub-Saharan Africa, India, Pakistan, parts of Southeast Asia, it's also a challenge in Europe, in North America, and that's why we see a lot of NTN activity there as well. So this is very much a global challenge. If I shift gears towards the business side and enterprise with IoT, this is more of an emerging thread to the discussion, and I think this is actually really interesting. So apologies, some of these names aren't showing up on the chart. We can send that afterwards. But through our modeling, we think about 2 billion IoT devices are addressable through satellite-enabled connectivity. That's things like weather sensors, it's sometimes low power other monitors, solar farmed, wind farms, oil and gas installations, mining rigs, and of course automotive and trucking / logistics. I think we're seeing a lot of new business models to bring this connectivity that hasn't been previously available to these businesses. And a lot of telco operators who are in the game are looking to monetize these relationships with satellite partners in this B2B space just as much as they are consumers. So when you look at that on a sell-in basis, we think this is worth an incremental, as an additional $10 billion per year by 2035. And that's sort of 20 to 25% of the existing IoT connectivity revenues. So really significant uplift if that's translated. One of the other, just to transition to some of the technology improvements that have been filtering through, you might have heard of the term direct-to-device, or D2D. This is one of the sort of emerging, or re-emerging, I should say, trends where direct-to-device offers the ability to beam a signal directly to someone's device. It does what it says on the tin, rather than the need to have receiving equipment, a satellite dish that then goes through a Wi-Fi hop to reach its intended users. Now, why does that matter? Well, it increases the efficiency that the signal can be delivered, so it's a lower cost and set of integration with terrestrial base stations. That speeds the time to market, but it also means that there's a lower TCO for consumers, which, all else equal, is a good thing for driving uptake. Now, I say this isn't new, but what's really changed here is that the enshrining of NTN standards in 3GPP with release 18 and through an update to release 18 to come, that really increases massively the addressable market that's in play here. Mobile operators are very, very aware of this set of economics and attuned to being able to capture that opportunity. And what we're showing here is a selection of the partnerships that have been formed across the world between major telco operators and their satellite partners to make the point that A, this is a global phenomenon, and B, it's a scaled phenomenon. So the size of the tiles in this tree chart actually reflect the subscriber footprints of the operators who are in a given partnership. You can see Vodafone there, covering its European and African businesses with Safaricom and Vodacom, over 330 million people. And likewise, OneWeb and Bharti, a similar amount, and on down. And so this actually totals, if you look at all the partnerships we track, you have a subscriber footprint of around 2 billion people, which is coming up on a third of the global base overall. So it's material. Now, that doesn't mean all of those people, of course, are connected into satellite. It's the addressable base. But that has more than doubled in a year. So it gives you a sense of the momentum that we're actually looking at here. And I should say many operators are choosing to partner with multiple satellite groups. So there's a lot of variety and pragmatism in how this is being done. So from a financial point, a lot of people ask the question, how does this get monetized and what does that add up to? Maybe I'll take those in turn. So most of the business model relationships that we see are on a wholesale partnership basis, where satellite groups or HATS operators are providing backhaul or fronthaul connectivity to a telco operator, who then continues to own that customer relationship. It's not always the case, but that's the predominant means. Starlink is attempting a direct-to-consumer model in many countries, targeting a broadband market, but most tend to work on the wholesale market, and that's because there's a symbiosis. There's a complementarity of satellite or non-terrestrial network connectivity to ground coverage and ground networks. So the second thing is, how much does it add up to? And we've done some modeling, and I wanted to share that here. We think that when you feed through the use cases and make assumptions on when constellations are launched, as well as devices compatible, you get to a sort of $30 to $35 billion per year addressable through satellite-enabled connectivity by 2035. That splits out about 60% consumers, a third business, and the rest is government and defense. But most of that should filter through in the late 2020s and early 2030s, given the timing of the launches. So it's a material uplift. It's about 1.5 to 2.5% of existing industry revenue. So it's something that's getting a lot of attention. And I think the last slide here I want to show is the outlook and sort of the set of questions. Now, I won't go through all of these, but I think these help guide the way we think about where this area goes. There's technology questions. Can satellites get beyond the current deliverable speeds, about 5, 6, 7 megabits per second? Clearly, there's talk of 5G networks in the sky, but that throughput isn't actually possible in terms of comparable LTE and 5G networks on the ground. Does that get bigger? There's a chipsets and handsets integration and a whole coalescence of the device ecosystem. On the business model, I think there's questions about, do other companies go down a retail route rather than the wholesale route? We think that's not likely, but some are experimenting with it. And then on the regulatory side, I think there's still open questions around the spectrum points, particularly where companies are attempting to share terrestrial spectrum that has technical challenges associated with it. And then looking ahead, enshrining standards in latter generations of 5G and into 6G. We think this is here to stay. This is a phenomenon that is here to stay and that will evolve. But I think there's a lot of fine-tuning to come on these questions. So we'll be following it very closely. So that's the sort of content I wanted to share. This is a little bit about us, but I will be back when we get to the Q&A. For now, I wanted to hand over to Rob Maunder from Accelercom. So, Rob.
Thank you, Tim. And thank you all for having me. I'm the founder and the CTO of Accelercom. I'm here to talk today about the 5G satellite testing challenge. The context for this is the momentum that we've seen pick up over the last year in particular for 5G NTN systems, and Tim, you spoke to that very nicely, I thought. We're seeing this interest from handset vendors, equipment manufacturers, satellite operators, and they're all eager to engage with mature solutions. So this presents new opportunities and new challenges. In our previous webinars, we spoke about the integration challenges that we've been addressing at Accelercom, and in this presentation we'd like to focus on the testing challenges. So on this slide, I present a bit of an overview for the talk I'll give just now. We'll start by talking about the radio challenges for the layer 1, the physical layer of a regenerative low Earth orbit 5G NTN satellite system. Then we'll look at the Accelercom solution for this. We call it LEO-Fi. And then we'll talk about the testing methodology. And this is hierarchical. So we have different bits of testing that we perform at different levels to make sure we get into every nook and cranny and get all the thoroughness there. And at the end, I'll offer some summary thoughts. So first of all, we'll just have a look at the non-transparent low Earth orbit satellite architecture. In the figure on the left-hand side there, you can see the contrast between LEO and medium Earth orbit and geostationary orbit. They're characterized by these different altitudes. And the low Earth orbit, you can see, is much lower in the sky than the other options there. That has advantages in terms of the link budget, the reduced path loss, stronger signals, and lower delays, but challenges in that the satellites move quickly across the sky, and so a constellation of satellites is needed in order to give continuous coverage. On the right-hand side here, you can see the architecture for the non-transparent satellite deployment. This is also known as regenerative. And the idea here is that you put the GNO-B, the 5G base station, onto the satellite. And that's in contrast to a transparent architecture where instead the GNO-B is situated in the gateway on the ground, and then the satellite acts as a relay. So in the regenerative non-transparent architecture, the satellite is doing all of the GNO-B functions. There's various bits of filtering and frequency conversion. There's demodulation and decoding, and there's various layer 2 and perhaps even layer 3 switching routing activity as well. And yeah, so the key benefits of the non-transparent regenerative architecture over the transparent one is the shorter round-trip delay between devices on the ground and the GNO-B, which is in the satellite. And this leads to improved quality of service and also allows the decisions that the GNO-B makes to be based on more recent up-to-date information, and so that leads to better performance. On this slide, we talk about the challenges that the radio environment presents for a low Earth orbit satellite. We'll make reference to the diagram on the left there, where you can see a LEO satellite transitioning across the sky and serving, in this example, a couple of user terminals there on the ground. And as the satellite moves across the sky, it's shaping a beam to provide continuous coverage on a certain part of the surface of the Earth. But as the satellite moves, the shape of that beam is changing, and so there are challenges associated with handing over between different beams, and then also handing over to different satellites as they come into view. The propagation delays relative to terrestrial networks are long, and so a challenge of this is the amount of time it takes for retransmissions, the hybrid automatic repeat request process to resolve, and there may be many active HARC processes within a particular user equipment at a time. And this can even lead to a stalling problem where the user equipment runs out of slots for HARC processes. And so this has to be very carefully managed. It motivates the targeting of much lower block error rates in the communication channels. In terms of the delay, there's an added challenge that different user terminals at different locations within a beam on the surface of the Earth will experience slightly different delays. And this can mean that their signals are unsynchronized when they're received at the GNOB, and that's challenging, particularly in resolving random access when a handset wakes up and connects to the network. The satellites are moving quickly across the sky, so this leads to Doppler shift, which can be as much as plus or minus 48 kilohertz for a low Earth orbit in the S-band. And this amount of Doppler shift is large. It's larger than the 5G new radio synchronization was originally designed for. It's larger than the subcarrier spacings that are used in the OFDM waveform for S-band, for example. And further than this, the Doppler changes. As the satellite moves across the sky, it will start off at a high Doppler shift of plus 48 kilohertz, and then transition over the course of a few minutes to minus 48 kilohertz. So this is a challenge that has to be dealt with. As the satellite appears over the horizon or disappears over the other horizon, then line of sight probability is low, so this presents link budget challenges. And even when the satellite's overhead, there's a high path loss owing to the propagation distance. And then on top of all that, there are challenges, particularly in KU and KA bands, FR2, relating to atmospheric and weather effects, which cause the signal strength to fluctuate. So what I'd like to do on this slide is introduce LEO-Fi, which is Accelercom's solution for the physical layer of a regenerative GNOB 5G NR waveform. You can see on the right-hand side here a block diagram for LEO-Fi integrated into an evaluation onto an evaluation board. I'll talk through some of the advantages of the system before detailing the block diagram for you there. So key aspect of this is that it's performant. We've done a lot of work in optimizing the signal processing that's performed in the physical layer here to give high throughput, to achieve low block error rates. I spoke earlier about the challenges of HARC and low power consumption. The business model is one of licensable IP. So we provide the software and the firmware that runs on commoditized space-hardened devices, and we can provide that at a complete layer 1 level, or we can provide components, and we do so to OEMs and operators and semiconductor companies. It's a heterogeneous architecture, so we use CPUs for software processing. In this solution, it has FPGAs for hardware processing, and by leveraging the acceleration from FPGA and the flexibility from software, we can get a best of both worlds approach to the implementation here. The design is compliant to various standards, so 3GPP, and I'll talk more about some of the 3GPP standards on testing later on, but the interfaces are also compliant to ORAN, and small cell forum have a NFAPI interface, which we use at the top of the block diagram over there for interfacing with layer 2. The architecture is flexible and scalable, so we can address SNL band applications in FR1, as well as KA and KU band applications in FR2. And the IP, the code is all portable, so it can run on various different FPGAs, and also it can be synthesized into an ASIC as well. And we supply all of the IP integrated. We use a ZCU111 development board, which has a ZU28DR RF SOC from AMD running on there. And our integration includes not only the signal processing, but also the RF interfaces and the layer 2 interfaces as well. So looking at the block diagram here, you can see at the heart of it there are a variety of different channels in the uplink and the downlink. There's 7 in total, you can see in the middle there. And those represent the Hi-Fi, which is the core of our Leo-Fi solution. On this evaluation board, we have also integrated Lo-Fi, provided by a partner company. And then at the bottom of the block diagram, you can see RF interfaces for both the downlink and the uplink. And at the top of the diagram, you can see interfaces with layer 2 for NFAPI. And all of this is accelerated by hardware accelerators for forward error correction, which you can see on either side of the diagram there. So we'll start with the testing of those forward error correction accelerators. Acceleration is necessary for forward error correction because it's the most computationally intensive part of the signal processing in the layer 1 of the 5G new radio waveform. And this includes both LDPC, which is used in the data channels, and polar coding, which is used in the control channels. And the performance that you achieve with these is really critical to the quality of service that the system can deliver. So in Leo-Fi we have accelerators for LDPC and polar, and there's also the ancillary components such as CRC and rate matching and HARC and so on. We also have software models that are bit accurate to the hardware accelerators, which we've integrated into the software part of Leo-Fi as well. And this is key to the testing approach that we use. So you can see on the diagram here those hardware accelerators, those software models, and a test environment in the green blocks where we generate test vectors at the input to both the hardware and the software implementations, and then a comparison which is performed at their outputs to make sure that both are giving exactly the right answer, the same answer as each other. And we use this environment in a couple of ways. The first of which is constrained random testing. So what this will do is it will run a wide variety of different test vectors to get into all the corner cases, all the unusual circumstances that the FEC codecs can be required to operate in, and make sure that we have conformance to the standard and a perfect match between the hardware accelerator and the golden reference model. We use a UVM methodology for testing this, and we can run that in simulation. We can also run these comparisons and tests in real time on the development FPGA board as well. And then a second way that we use these models is for performance characterization. So we can use Monte Carlo simulation to characterize the block error rate of the decoder blocks here. And we can, as a benefit of running this on the real hardware at real time, we can characterize the block error rate at very low levels where errors only occur 1 in a million times, for example. And that's really important in non-terrestrial network applications where reliability is so important, particularly if you want to avoid long latencies that come from extended HARC processes. So instead, it's preferable to operate at a lower block error rate and have the transmissions work first time. And then on top of all of that, all of this testing is automated. We have a continuous integration and continuous deployment environment based on Jenkins, which will automatically run all of these tests whenever a colleague makes a change to any line of code and then raises a pull request on Git, then automatically all of the tests get run and a report gets written automatically to confirm that that change hasn't caused any regression. And we run all of these tests also on a daily basis as well. So having spoken about the testing of the forward error correction blocks, now we can progress on to the next level, which is looking at the various different channels in the Hi-Fi of the physical layer. And you can see in the diagram here, there were 3 channels in the downlink, the PDSCH data channel, PDCCH control channel, and the SSB broadcast channel. And then in the uplink, you have the push data channel, the push control channel. The Pratch is used for random access, and the SRS is the sounding reference signal. So for each of these, we have a test environment where we generate test vectors at the input to those channels, and then we have at the output, we have a test framework that will confirm that the results are as expected, and we can also measure performance here. And what we're using at the southbound bottom end of these block diagrams is an emulation of a U equipment to confirm that we get a perfect match between the G-No-B operation and the UE operation. And again, there's two types of testing that are performed here. The first is a constrained random testing, testing all of the different use cases across a comprehensive test plan, which considers all the features that we have integrated into the system and also considers all the combinations of parameters that we're supporting. And then also Monte Carlo simulation, again to measure the block error rate and test the performance there. And we can run all of this in simulation on x86 and ARM servers, or we can run this also on the development board using the FPGA forward error correction accelerators and running in the embedded ARM processors that are there on that ZU28DR device. And as before, all of this is automated, CI/CD automation, so any change of code to any line in the code there triggers automatically the regression testing of all of this. Looking at the next level now, this is end-to-end real-time L1 testing. So what we have here is Leo5 running on an evaluation board. It's the ZCU111 that I highlighted earlier, running with real test equipment. So we have signal generators and channel emulators for testing the uplink and signal analyzers for testing the downlink. And so those are connected to the RF interface of the ZCU111 board. In the layer 2 side, we have developed a test application which we call TestMac. We couldn't find a solution that met all of our requirements off the shelf, so we had to develop this from scratch. What it does is it emulates the operation of the layer 2 and it generates the NFAPI command which control the layer 1, the physical layer. And not only that, it also TestMac can also generate Skippy commands which feed directly into the test equipment to control their operation as well. And in this way we can automate the various different tests to make sure that the operation of the physical layer and the operation of the test equipment is synchronized and aligned so that they're testing against each other in the correct way. And it's all automated. You can run through a sequence of tests and you can watch the test equipment and see it flicking through all these different modes and different waveforms as it progresses through the suite of tests. Again, we have constrained random testing, which validates all the supported features, the combinations of parameter values. We also have testing against the 3GPP requirements. So these are defined in 38.181 for NTN systems. So there are TX tests, transmit tests, which test things like the out-of-band emissions of the transmitter, receive tests, which will test things like the receive sensitivity, and then performance tests, which consider the block error rate, for example, or the false detection rate, for example, in the Pratch channel. And these tests include NTN-specific things like the Doppler frequency and the propagation delay. And as before, all of this is automated using CI/CD. It's all controlled by Jenkins and runs overnight and whenever a colleague changes a line of code. So here we have a photograph which kind of illustrates this. This is not the racked up test platform that's run automatically. This is one that we've got for demonstration manually. But it's showing a variety of different components there. On the right-hand side, you can see a laptop which is running the TestMac software, and that's connected by an Ethernet cable to the ZCU111 board, which you can see in the middle of the photograph, and that's carrying the NFAPI commands and traffic. The ZCU111, you can see in the middle there is a heat sink and a fan. Underneath that is the ZU28DR FPGA RF SOC device. And the software is running on the embedded A53 processors that are in there, the LDPC accelerator, the Polo accelerators, and the Lo-Fi are running on the FPGA part of this. And on the left of that board, you can see a breakout where there's lots of different SMA connectors, and one of those is connected to the signal analyzer you can see in the left of the photograph, which is completing the downlink testing that I described before. And then a final level of testing is end-to-end real-time G-No-B testing. So here the Leo5 is integrated with layer 2 and layer 3 from a partner company to build a complete G-No-B. And this is controlled by a 5G core. And at the RF interface, it's passed through a channel emulator, which can emulate various different NTN channel conditions, and into a UE simulator. And with this test environment, the G-No-B can be tested fully end-to-end in a simulation of a real satellite scenario. This scenario considers the transition of a low Earth orbit satellite from one horizon over to the other, with the Doppler frequency varying from plus 48 kilohertz to minus 48 kilohertz across that transition, which takes several minutes. It includes the Doppler effect, the propagation delay, fading and noise, path loss, all of these different effects. And what's been demonstrated with this approach is the UE simulator being able to connect to the GNOB and sustain full bandwidth uplink and downlink traffic and video streaming across that duration of that transition. So with this level of maturity and this amount of testing now, this GNOB is ready for launch on a satellite. So just to conclude for you here, we feel rigorous testing of the 5G physical layer is crucial for any 5G NTN system, as well as its integration into the GNOB and the testing at the various different layers that we've described in this presentation here. It's not easy to do this kind of testing. There's a lot of work that has to go into building a dedicated test environment, to build a comprehensive test plan, to explore all the different combinations of parameters, and to work through that sequence of tests, which has to include both constrained random testing and also Monte Carlo performance characterization. Alongside all of this has to be considered NTN specific challenges such as Doppler and delay and path loss. And now, having gone through all this process, we feel that the Accelercom LEO-Fi L1 has been proven through thorough testing at multiple levels and is now ready for deployment. So thank you. Michael, I'll hand back to you.
Rob, thank you so much for that. I'll let everyone just pause for a moment and take all of that in, because there's a lot of information there, and you've definitely covered a lot of the key challenges that I don't feel are talked about very much in this new wave of satellite. Just a reminder to the audience, we also want to hear from you. I know I've got a few questions after that, and if you do, we have some time now to go over those. So if you just pop those into the box underneath the main presentation screen, we will do our best to get to them. But Rob, Tim, I hope you're both well rested, because we've got a few coming in already. I think there's two elements. There's the first one that I'd like to cover. I think there's sort of two elements to, so I might split this. Tim, I think perhaps I'll give this one to you initially, and Rob, if you want to weigh in, you do feel free. But the question is, can 5G compete favourably with fibre optics, because 5G operates ultra-high frequencies and with a short range? So Tim, I just feel that maybe that's for you.
Yeah, I mean, so it can. I think it depends on the deployment posture and specific situation. But I think what we've seen is, as we mentioned, some significant performance upgrades to the NTN signal strength, round trip latency, and other kind of factors that measure performance. And so, but what fundamentally the satellite there is as a complement to ground 5G and other mobile connectivity. So it's there to play a role, but not to replace anything.
And Rob, just to bring you in for this sort of second part of this initial question, which was also, can a 5G satellite be deployed in densely populated metropolitan areas? I think that's a question of coverage, which you'd sort of touched on during the presentation.
Yeah, so indeed 3GPP in their study on non-terrestrial networks have considered applicability in urban environments. They've defined channel models, which are non-line of sight channel models, which would associate with the shadowing that's caused by buildings, for example, blocking the line of sight to the satellites. So there is provision for this kind of thing in the 3GPP work that's been done. My feeling is that in those environments there is likely to be a terrestrial network that's deployed, and that, as Tim says, these things are complementary. It may be that a handset device will make a decision about which network to use as appropriate in a variety of different situations, and quite naturally you might expect that the terrestrial networks gets greater use in the urban environments, whereas the satellite gets greater use in the remote and rural environments.
Absolutely, and I know that most sort of coverage of the sector so far, this resurgence in satellite connectivity has been, as Tim had mentioned, sort of addressing coverage gaps, and that is typically, we're looking at remote regions just from an economic standpoint, where it might not be, viable to be deploying regular mobile and terrestrial-based solutions. So. The next one, I think, Rob, this is for you, but again, Tim, feel free to weigh in afterwards. But the next up is, what elements do you consider important to validate designs for better performance of the 5G physical layer?
Right, so I would say that you have to be thorough and comprehensive. So I would say the answer is all of the elements. Some elements which are particularly important for dictating the quality of service that's delivered by a solution. Amongst those, I would say, channel coding in particular. This is the most computationally intensive part of the signal processing, and so it deserves a lot of attention. Certainly our conversations with the satellite industry often start with a conversation about LDPC performance. The key aspect here are delivering low block error rates without suffering from error flaws. And there are code design aspects which 3GPP considered in the design that are relevant here, but there's also implementation aspects. The design, the LDPC on a chip, has to carefully consider its performance in the presence of very, very rare but still important events which are characterized in a block error rate analysis. And yeah, block error rate curve, if you were to plot one, you can draw them all the way down to 10 to minus 6, 10 to minus 7 block error rate, and that's still relevant in NTN applications. But at that point, you're characterizing events that happen 1 in a million times. And so a test environment that allows you to run a very long soak test to observe these rare but important events is quite important.
Thanks, Rob. And Tim, do you want to weigh in there, or shall I ask you another?
No, I think Rob's been comprehensive there.
Cool. Okay, well, next up, looking at, again, it might be one for Rob, the transmitted power in the satellite must be very high so the receiver gets the data. So what about the uplink?
So if you look at TR, I think it's TR 38.811, this was the study item that 3GPP did on NTN. There's some good coverage in there about the link budget, and indeed in the downlink, the satellite transmits at high power, so that the signal that reaches the user terminal, having gone through all that path loss and propagation delay, is strong enough for the signal to receive, for the user terminal to receive, and so high transmit power is important in the downlink. In the uplink, you can't expect a handset, for example, to transmit at a high power, and so indeed the question is asking, what do we do about that? And the answer is again, it falls on the satellite. The satellite has to have a very high receive sensitivity, and in the link budget analysis you can find in 38.811, you can see some indicative numbers for this. But indeed, it is all of the complexity there is weighed onto the antenna system of the satellite, such that it can essentially hear the very weak signals that are transmitted by the user terminals.
Okay, thank you. I'm probably not going to pronounce this properly. Could you highlight the PRACH differences between non-terrestrial networks with terrestrial networks, and are the non-terrestrial networks fundamentally different from terrestrial of both 5G and 4G? So I think, Rob, first, if you could correct my pronunciation there, that would be helpful.
Yeah, no problem. Some people call it PRACH, some people call it PRACH, and I'm sure there's plenty of other pronunciations as well. So this is all about how a user terminal connects to a network, and how you can establish the timing error and compensation that's needed, the so-called timing advance. So in terrestrial systems, there is a long propagation delay, and compensation is needed at the user terminal. It has to transmit in advance of when the satellite is expecting to receive, in any case, but there will likely be some error on top of that, partly because of the complex mathematics involved, but also because the beam that the satellite is casting on the surface of the Earth is large, and different user terminals at different locations within that beam will have different timing advances needed. So the p-watch allows that error to be estimated, but that error can be large. And so what this motivates is the use of long p-watch sequences in non-terrestrial network applications. 3GPP defines a variety of different p-watch waveforms, including long ones and short ones. It's those long ones that are most relevant in non-terrestrial networks. But in 3GPP as it stands, those long sequences are only used in FR1, the sub-6 gigahertz carrier frequencies that are used in the S-band and L-band for NTN. So for KA and KU band, there is some work going on looking at what do we need to do about p-watch in these applications. Do we need longer sequences to cope with the sort of delays and timing advance errors you might have in these satellite applications?
Okay, that's a similar vein, and I'm sorry if you're feeling left out, Tim. But Rob, I think again, perhaps you might want to take the lead on this. What are the main challenges at the GNB when there are multiple UEs spread across the cell of beam, which produce these delay and Doppler variation? Or is the assumption that the UE has pre-compensated the delay and Doppler to relevant levels?
Yeah, so there's a variety of different solutions that can be considered here. I've spoken a little bit about some of them just now in terms of the delay aspect. In terms of the Doppler, there is compensation you can do at the UE. There's some you can do at the GNOB, and indeed you can do some at both. My feeling is that it is necessary to do at least some of the Doppler frequency compensation at the UE, because of the geometry, and you may have different UEs at different locations within a beam having different Doppler frequency when communicating with the same serving satellite. If the UEs didn't compensate their transmissions, then they would be received on slightly different frequencies and could overlap each other, and there would be nothing that the GNOB could do in terms of compensation to correct that. And so the solution to that has to be that the UEs pre-compensate with knowledge of where the beam is pointing towards on the surface of the Earth and where they are inside that beam, as well as the motion of the satellite and their own geographical location and so on. So the compensation for both the Doppler and the delay is really important. The 5G waveform just won't cope without the compensation being applied.
Excellent. The next one is, okay, Tim, we can bring you back in. I think I'll give you this one. The satellites offer the potential to expand 5G coverage to remote and underserved regions, as we mentioned. Areas in which the population, as students, areas in which the population doesn't have access to the internet, and therefore academic, business development, and so on. Based on this reality, are there alternatives not only based on LEO but also MEO, and what are the advantages and disadvantages of each?
Well, you know, I think there's a plethora of satellite constellations that exist both at the LEO and MEO altitudes. They do different things and they bring different advantages and trade-offs. I think, you know, obviously the higher up you get, the wider the ground coverage is, but the longer the latency. The advantage we've seen from updated LEO constellations of late is that, you know, they have been able to get that latency down quite a bit. You know, historically satellite latency has been around 600 milliseconds. Now that's come right down, and you know, that has enabled, you know, higher speed service to be delivered to those populations. What I would say is that there are still challenges in augmenting the capacity, so that when, you know, a lot of people are trying to connect to the service on the ground, which may happen as these constellations mature, to avoid congestion in the service and to maintain the throughputs that are advertised. You know, there's still work to do there. I think there's been, as Rob's very, you know, ably alluded to, a lot of improvements in the beamforming technology to and part of that's using sort of a lot of AI algorithms a lot of improvements in beamforming to ensure the signal is directed to the place and dynamically, but the capacity increases, will be important to the payloads, looking ahead.
Okay, Rob, do you care to weigh in there?
Yeah, I suppose in comparison between LEO and MEO, some of the differences on the technical side would be the longer propagation delays to the MEO, the greater path losses. I think these would preclude the use of handsets and IoT devices, but more sort of fixed, ships and aircraft and buildings, antenna systems may be able to cope there. The advantage of MEO is the satellites move more slowly across the sky. Perhaps that means you can have a constellation having fewer of them. So there's advantages and disadvantages there.
Absolutely. I suppose we wouldn't have the mixture that we have of GEO, MEO and LEO if they all could do the same thing. Back to the testing, Rob. Question: what is important to test other than the PHY layer? I'm guessing physical layer, mainly considering E2E services.
Yeah, certainly. In this presentation we have focused on the layer 1 testing. And I showed a block diagram with the layer 1 integrated with layer 2 and layer 3 and the 5G core. Of course, there's similar amounts of testing that are necessary in each of these levels, and there will be a hierarchical approach adopted there, no doubt, that considers individual functions with individual test plans, building up to the complete layer 2 level, the complete layer 3 level, and then their integration as well. I think that a measured approach to testing in general is a hierarchical approach where you put a lot of detail into the small pockets of focus, and then in successive layers you can build on the testing that has been done intensely at the lower layers.
Sorry, forgive me delay there, I missed the mute button. Okay, the next question is non-transparent or regenerative satellite, in non-transparent or regenerative satellite, excuse me, why is a round trip delay shorter compared with ground station based G node B? Shouldn't this be longer due to the longer propagation time?
Right, yes, okay, so let's consider the HARC process. So what happens here is a user terminal, let's assume we're talking about the uplink, a user terminal will transmit a message, and that will get to the G node B. The G node B will consider whether it has successfully decoded the message or not, and if not, it will send a repeat request message back to the UE, and then the UE will transmit another attempt at the message. The G node B will then receive that and again consider whether it's now decoded successfully, and if not, then the process continues. And so you can see that when you're dependent on HARC, terrestrial network systems, they're using this for about 10% of all the traffic. They're relying on retransmissions. So in that kind of regime, the distance between the G node B and the user terminal is really important because it dictates how quickly you can progress through those successive hops and retransmissions. So if the G node B is on the satellite, then that's half as much back and forth as compared with the G node B being in the ground station. And so that's where the quality of service improvement comes from in terms of the delay from having the regenerative architecture.
Great. Well, I think we're sort of pushing the 50-minute mark, so that might be a good time to wrap things up. So Rob and Tim, thank you both very much for a terrific discussion on addressing the E5 satellite testing challenge. And thanks to you, our audience, as well, for all of the great questions, some of which were quite tough, I think. So you've made most of Rob's expertise there. It's good to see such interest in this sector, guys, it really is. A replay of the session will be available shortly, and if any further questions, you can, of course, contact Accelercom and the GSMA Intelligence through their website. So Rob, Tim, thank you both very much once again.
Thank you.
And thanks to our audience and all of our hosts. Thanks, everybody. Goodbye.